Hey there, science fans! Today we're diving into the fascinating world of analytical chemistry. This branch of chemistry is all about understanding the composition of materials. It's like having a superpower that lets you see the invisible world of molecules and atoms. Imagine being able to tell exactly what something is made of just by analyzing it. That's the magic. Analytical chemistry is like being a detective, but instead of solving crimes, we solve chemical mysteries. Think of it as a scientific investigation where we gather clues from the smallest particles. We use our skills to uncover the secrets hidden within substances, whether it's identifying unknown compounds or determining the purity of a sample. We figure out what stuff is made of and how much of each ingredient is in it. Pretty cool, right? Imagine baking a cake and knowing the exact amount of sugar, flour, and butter in each slice. That's what analytical chemists do, but on a much more complex level. They measure and analyze substances to ensure accuracy and consistency in everything from pharmaceuticals to food products. Analytical chemists use a variety of tools and techniques to identify and quantify chemical substances. These tools include spectrometers, which can measure the light absorbed by a substance, and chromatographs, which can separate mixtures into their individual components. Microscopes allow us to see the tiniest details, and other advanced instruments help us understand the chemical makeup of materials. These techniques can be used to analyze everything. For example, air quality tests can detect pollutants and help us understand their impact on health. Analytical chemistry is essential for maintaining the quality and safety of our environment and the products we use daily. Analytical chemistry plays a vital role in many different fields, including medicine, environmental science, and food science. In medicine, it helps in the development of new drugs and the monitoring of patient health. Environmental scientists use analytical techniques to study pollution and find ways to protect our planet. In food science, it ensures that our food is nutritious and safe to eat. The applications of analytical chemistry are vast and impactful, making it a cornerstone of modern science. In analytical chemistry, there are two main types of analysis: qualitative and quantitative. But first, are you enjoying the video so far? Consider liking and subscribing so you can ace that chemistry class. Now that that's out of the way, let's get back to the video. There are two main types of analysis: qualitative and quantitative. Qualitative analysis is like figuring out the what in a sample. It tells us what substances are present, but not how much of each substance there is. A test confirms the identity of a compound. This analysis includes the description of a compound. Quantitative analysis, on the other hand, is all about the how much of a chemical substance is present. This analysis is all about numbers and statistics. It tells us the exact quantity of a particular substance in a sample. So, if we want to know how much sugar is in a can of soda, we would use quantitative analysis. To illustrate the principles of analytical chemistry, let's consider a delicious example: measuring the caffeine content in chocolate. That's right, chocolate contains caffeine. Caffeine is a bitter, white, crystalline compound found in coffee beans, tea leaves, and cacao beans, which are used to make chocolate. We all know that chocolate can give us a little boost of energy, and that's because of the caffeine. Now that we know chocolate contains caffeine, how much caffeine is present within a chocolate bar? To find out, we'll need to use some analytical chemistry techniques. Let's find out how to extract the caffeine and break it down in 5 steps. The first step in any analytical chemistry experiment is to obtain a representative sample. This means getting a small amount of the material we want to analyze that accurately represents the whole thing. For example, if we want to know the average caffeine content of a batch of chocolate bars, we can't just analyze one bar. We need to take samples from multiple bars to make sure we're getting an accurate representation of the entire batch. Is the chocolate bar homogeneous or heterogeneous? Does the chocolate contain any bits of peanuts, or is it 100% chocolate? Step 2. Sample preparation, from chocolate bar to test tube. Once we have our sample, we need to prepare it for analysis. This usually involves breaking down the sample into smaller pieces and removing any substances that might interfere with our measurements. In the case of our chocolate bar, we would need to grind it into a fine powder and then extract the caffeine using a solvent. Step 3. Chromatography, separating the caffeine. Now that we have our caffeine extract, we can start to analyze it. This is a crucial step in understanding the composition of our sample. By analyzing the extract, we can determine the purity and concentration of caffeine, as well as identify any other compounds that may be present. This information is essential for various applications, including quality control in the food and beverage industry, pharmaceutical research, and even forensic science. One common technique for separating and identifying different components in a mixture is called chromatography. This is a powerful analytical method. It allows scientists to separate complex mixtures into their individual components, making it easier to study and understand each substance. There are several types of chromatography, including gas chromatography, liquid chromatography, and thin-layer chromatography, each with its own unique applications and advantages. Chromatography works by passing the mixture through a column filled with a material that interacts differently with different substances. This material, known as the stationary phase, can be a solid or a liquid. As the mixture, called the mobile phase, moves through the column, the different substances in the mixture interact with the stationary phase to varying degrees. These interactions cause the substances to move at different rates, effectively separating them as they travel through the column. Some substances will stick to the material more strongly than others, so they will move through the column more slowly. This differential movement is what allows us to separate the components of the mixture. For example, in our caffeine extract, caffeine molecules may interact with the stationary phase differently than other compounds, causing them to separate as they pass through the column. By carefully controlling the conditions of the chromatography process, such as the flow rate and temperature, we can achieve a high degree of separation and obtain pure samples of each component. This allows us to separate the different components of the mixture, including our caffeine. Once the separation is complete, we can collect the individual substances in separate containers for further analysis. This step is critical for ensuring the accuracy and reliability of our results. By isolating the caffeine from other compounds, we can perform more detailed studies on its properties and behavior. Chromatography is an indispensable tool in the field of analytical chemistry, providing valuable insights into the composition and characteristics of complex mixtures. Step 4. Measuring the caffeine. Calibration curves are a crucial tool in analytical chemistry that allows us to quantify the amount of caffeine in our samples with precision and accuracy. Once we have successfully separated the caffeine from the other components of the chocolate, the next step is to measure how much of it is present. This is a critical phase in our analysis because it provides us with the quantitative data needed to understand the caffeine content in our sample. The separation process ensures that we isolate the caffeine, removing any interfering substances that could affect our measurements. One way to accurately measure the caffeine content is to use a calibration curve. They are essential in analytical chemistry as they provide a relationship between the concentration of a substance and the response of the analytical instrument. This relationship is typically linear, making it easier to interpret the data and calculate the concentration of the unknown sample. A calibration curve is essentially a graph that plots the signal produced by a detector, such as a UV-vis spectrophotometer, against known concentrations of the substance we are interested in measuring. The x-axis represents the concentration of the substance, while the y-axis represents the signal produced by the detector. By plotting these points, we create a curve that can be used to determine the concentration of unknown samples. By measuring the signal produced by our caffeine sample, we can use the calibration curve to determine its concentration. This involves comparing the signal from our sample to the calibration curve and finding the corresponding concentration. This method is highly reliable and allows for precise quantification of caffeine in various samples. The calibration curve not only helps in determining the concentration, but also in validating the accuracy and precision of our analytical method. It is a fundamental tool in ensuring that our measurements are both accurate and reproducible, providing confidence in the results obtained from our analysis. Step 5. Interpreting the final results. How much caffeine is in your chocolate? Finally, we arrived at our results. So the question stands: how much caffeine is present within a chocolate bar? The final step in our analytical chemistry experiment is to interpret our results. Let's say we measured the caffeine content of our chocolate bar to be 10 milligrams per gram. This means that for every gram of chocolate we eat, we are consuming 10 milligrams of caffeine. We can compare this value to the caffeine content of other foods and drinks to get a better understanding of how much caffeine is in our chocolate. Conclusion. Let's revise each step in undertaking an analytical experiment. 1. Formulate the question. Translate general questions into specific questions related to chemical measurement. 2. Select the analytical procedure. Search chemical literature to find an appropriate procedure or devise a new procedure. 3. Sample. Select representative material to analyze. 4. Prepare the sample. Convert a representative sample into a form suitable for analysis. 5. Analyze. Measure the concentration of the analyte. The uncertainty of the measurement is as important as the measurement itself. Replicate measurements are essential. 6. Report and interpret. Deliver a clearly written, complete report of results, highlighting any limitations. Be sure the report is appropriate for the intended audience. Clearly written reports limit the chance for misinterpretation by those who use them. 7. Draw conclusions. At times, the conclusions may point you toward starting over and reformulating the question. The general steps in chemical analysis we went over are: formulate the question, select the analytical procedure, sample, prepare the sample, analyze, report, and interpret, draw conclusions. We've just walked through the basic steps of quantitative chemical analysis using the example of measuring caffeine in chocolate. We found out how much caffeine is present within a chocolate bar. Analytical chemistry is a fascinating field with precision that plays a vital role in our everyday lives. From ensuring the safety of our food and water to developing new medicines, analytical chemists are constantly working to solve important problems and improve our world. Keep asking questions and stay curious. Like and subscribe. Make sure to share if you found this video useful. Be sure to have a nice night and good night.